when it comes to the formation of colossal rogue waves that seem to appear out of nowhere and defy traditional expectations, many assume there's some mysterious, exotic mechanism at play. But here's where it gets controversial. Recent scientific research suggests that these monstrous waves are not as inexplicable as once believed. Instead, they often emerge from the natural physics of the ocean itself. Let me explain. Back in 1995, an extraordinary event shook the maritime world. An 84-foot-high wall of water slammed into the Draupner platform in the North Sea. This was the first solid evidence of rogue waves, a genuine oceanic phenomenon once thought to be part of maritime folklore. Such an event sparked decades of scientific investigation, aiming to understand how such extraordinary waves can form without violating the laws of physics. At the forefront of this research is Francesco Fedele, an associate professor at Georgia Tech's School of Civil and Environmental Engineering. His team has recently analyzed a vast collection of wave data collected from the Ekofisk platform, spanning nearly 2 decades, with the aim of uncovering the patterns behind these giants. In scientific terms, a rogue wave is typically defined as a wave crest taller than twice the average height of the surrounding waves, known as the significant wave height. They can arrive unexpectedly from unusual angles and can catch even seasoned mariners and offshore platforms by surprise. To better understand their origins, researchers examined over 27,000 half-hour wave records. Their goal: to compare how often extreme waves occur under different sea conditions, and how their probability is influenced by factors such as wave direction, frequency spread, and storm severity. What they found challenges some long-held assumptions. It turns out that the statistics of extreme wave heights align closely with what you'd expect from regular ocean physics, once you account for these factors. Previously, some scientists believed that a process called modulational instability, where energy from one wave amplifies neighboring waves, especially in long unidirectional wave trains, was a primary cause of rogue waves. However, the data from the North Sea suggests otherwise, especially considering that the open ocean environment distributes wave energy across many directions, not just one. In a multi-directional setting, the chances of continuous energy transfer from one wave to the next diminish significantly, reducing the likelihood that wave amplification mechanisms like modulational instability can dominate. The North Sea data shows waves arriving from many different angles, especially during storms. An important detail, because such spreading of wave energy disrupts the conditions needed for the classic instability to take hold. Instead, the research points to other mechanisms, such as linear focusing, where waves traveling at different speeds or paths converge temporarily, and second-order nonlinearities, which act like a sharpener for crests, being the main excuses for the biggest waves. These effects can enhance wave heights by about 15 to 20% over what linear physics would predict alone. A prime example that helped advance this understanding is the Andrea rogue wave observed near Ekofisk in 2007. This wave became a benchmark in the industry because it exemplified how often such giant waves could be encountered, providing crucial data for engineers and mariners to better assess risks. It helped transform stories from maritime folklore into concrete, measurable probabilities relevant to real-world operations. Furthermore, analyzing this extensive dataset clarified how wave characteristics evolve under different conditions. For instance, young seas driven by strong winds tend to show more skewed waves and larger bound nonlinear effects, which support the idea that bound nonlinearities, rather than intricate resonance phenomena, are more likely responsible for extreme waves in stormy environments. In recent years, advances in machine learning have also entered the scene. For example, a 2024 study used neural networks trained on buoy data to predict rogue waves with about 75% accuracy just 1 minute in advance, and around 70% accuracy 5 minutes ahead. This demonstrates that short-term warning systems are increasingly feasible, especially with better sensors and real-time data processing. So what does all this mean for maritime safety and engineering? Well, it's a strong message for ships, offshore platforms, and coastal risk management. Anticipate a wide range of possible extreme events driven by normal physics, rather than relying solely on mythic notions of rare, unpredictable monsters. Installing sensors and developing algorithms that recognize the early setup of these giant waves can provide crucial seconds to minutes of warning, literally saving lives. And here's a point that might stir debate. If rogue waves are mostly products of predictable physical processes rather than mysterious phenomena, does that diminish their danger? Or does it simply shift our focus from superstition to science? It's worth pondering whether our perception of these waves has been overly mystical, when in fact they are an expected part of the ocean's behavior, just at a scale that still commands respect.